We're now going to set up our unit circles to put all the values that we can calculate without our calculator. We're going to use our big ideas from 6.1, the big one here. Your coordinates on your unit circle are always cos theta, comma sine theta. So what it's going to look like is we're going to pick a certain area and always put our degrees there. So for example, this is 0 degrees in standard position or 360 degrees on the positive x-axis. Then if I move to my positive y-axis in standard position, can you see that that would be 90 degrees? In standard position, if I went to my negative x-axis, that angle would be 180 degrees. And if I went to my negative y-axis, I'd have 270 degrees. In green, we'll put those same angles in with radians. So 0 and 360, that would be 0 and 2 pi. 180 degrees is pi. Half of 180 degrees would be half of pi, or pi over 2. And 270 degrees would be 3 pi over 2. For our coordinates, we're going to label, because this is our axes family, we're labeling where the axes intersect the unit circle. And because this is a unit circle with a radius of 1, if this is your origin at 0, 0, does it make sense that this would be the point 1, comma 0? And this would be the point 0, comma 1, negative 1, comma 0, and 0, comma negative 1. And this opens up mental math without your calculator for sine and cos. For example, I can ask you, what's cos of 2 pi? So you look on here. Where's 2 pi? That's right here on our positive x-axis. According to our big idea, cos is your x-coordinate on the unit circle. So if I look at my coordinate on the unit circle, my x-coordinate is 1, so cos of 2 pi is going to equal 1. If you had your calculator and it was in radians and you wrote cos of 2 pi, your calculator would tell you 1. If I asked you sine of 90 degrees, go to 90 degrees. Look at your coordinate. Sine is the y-coordinate on the unit circle. So sine of 90 degrees will equal 1. Sine of pi. Go to pi, y-coordinate is 0, so sine of pi will be 0. Cos of pi would be negative 1. And you can figure out all of those values for sine and cos just by looking at your coordinates. From there, we can also use one of our big ideas that tan is sine over cos to figure out tan of each of these angles. So if I would do tan of 0, tan is sine over cos. 0 over 1 is 0. If I go over here and do tan of pi, again, tan is sine over cos, which is your y-coordinate, divided by your x-coordinate. 0 divided by negative 1 is 0. When I go to calculate tan of pi over 2, sine over cos for tan, I now get 1 over 0. What does that equal to? If you try it on your calculator and you do 1 divided by 0, what's your calculator going to say? It's going to give you an error because you're not allowed to divide by 0. So what do we write here? We just say that it is undefined. It is not possible. And same thing if you would do tan of 3 pi over 2, it is also undefined because you would have negative 1 divided by 0. This is our first family of values, all the values on the axes. For our second family, for our 45-degree family, or pi over 4, did I go too fast? Anybody need to go back? Okay, no problem. For our second family, you've got some space right up here. What I'd like you to write is special triangle for pi over 4 or 45 degrees. In order to label things on the unit circle, we need to know sine and cosine, because cos is the x-coordinate and sine is the y-coordinate. So if I draw a triangle and I want to find sine and cos, it's going to be a right-angled triangle because I know that sine is opposite over hypotenuse and cos is adjacent over hypotenuse. And if I want to make a special triangle for 45 degrees, well, one of the angles has to be 45 degrees. What's the other angle going to be? In that triangle. So in that triangle, if one of the angles is 45 degrees, it's a right angle triangle. What's our other angle going to be? 45. Because it has to add up to 180. What kind of triangle is this, besides being a right triangle? What's the name of this triangle? And what are the properties of that special triangle? Yeah, it's an isosceles triangle, and not only are the two angles the same, but two of the sides are the same. Now, the power of trigonometry. If you have 45 degrees, sine of 45 degrees stays the same no matter how big or how small that triangle is. It doesn't matter. So what we can do is we can pick any length that we would like for this side. I could pick 1, I could pick 2, I could pick 200. Now, for doing math, maybe I'll choose 1 because it's nice. You could choose any number. If you do a squared plus b squared equals c squared, what's the length of the hypotenuse? Square root of 2. And if we have the square root of 2 there, we now have enough information to figure out what's sine of 45 degrees, what's cos of 45 degrees, and what's tan of 45 degrees. Well, sine of 45 degrees is the opposite side over the hypotenuse. Our opposite side is 1. Our hypotenuse is root 2. And on our unit circle, we are going to rationalize the denominator. It would be all right to leave your answer like this, but just a reminder of how you rationalize your denominator. You would multiply top and bottom by the square root of 2. And it would give you square root of 2 over 2. Cos of 45 also is going to be 1 over root 2. So I'll just write that rationalized already as root 2 over 2. And what's tan of 45 degrees? Opposite over adjacent. Tan of 45 degrees is 1. So now when we go to label things on our pi over 4 or 45 degree family, what makes something a family of angles is all of their reference angles are the same. So this angle is 45 degrees. This angle here, if its reference angle is 45 degrees, I would go 180 minus my reference angle. I would get 135 degrees. So use your reference angle. You have a 10-second head start to finish the other two in degrees. How'd you do? Did you get 225 degrees and 315 degrees? Now we do the same thing in radians. If the reference angle is pi over 4, well, in quadrant 1 it would be pi over 4, exactly the same as your reference angle. In quadrant 2, well, in radians you'd have to do pi minus pi over 4. How do you subtract fractions? You need to get a common denominator. So 4 pi over 4 minus pi over 4, that will give me this angle as 3 pi over 4. Again, I'll give you a head start to do the last two in radians. How'd you do? Did you get 5 pi over 4 and 7 pi over 4? Again, for that 7 pi over 4, if you did it in degrees, you would have done 360 minus your reference angle. In radians, I would do 2 pi minus my reference angle. Again, I need a common denominator. So that would be 8 pi over 4 minus pi over 4, which would give me 7 pi over 4. Label your coordinates where those angles intersect your unit circle. Again, any point on the unit circle is cos theta comma sine theta. So since cos theta is root 2 over 2, and sine theta is root 2 over 2, our coordinates in quadrant 1 are root 2 over 2, comma root 2 over 2. If you use your reference angle, all of these triangles are identical. They all have the same reference angle. They all have the same sine, cos, and tan. So as a result, the coordinates here are also going to be root 2 over 2 and root 2 over 2. But according to your cast rule, cos is negative in quadrant 2 and sine is positive. And if you think about coordinates, if I have a coordinate here, my x value has to be negative. My y value is still positive. So your coordinate system also explain the cast rule. The reason why cos is negative in quadrant 2 is because your x coordinates are always negative in quadrant 2. And the reason that sine is positive in quadrant 2 is your y coordinate is always positive in quadrant 2. So the unit circle and the big idea that x coordinates on your unit circle are cos and y coordinates on your unit circle are sine explain the cast rule and why some things are positive and why some things are negative. And in quadrant 3, can you see that both your x and y coordinates would be negative? So the values stay the same. But now they're both negative. And in quadrant 4, your x value will be positive, but your y value will be negative. And for figuring out tan, well, from our special triangle, we know that tan of pi over 4 is going to equal 1. Can you see that you could use your coordinates to figure that out as well? Root 2 over 2 divided by root 2 over 2 is 1. And in quadrant 2, tan of 3 pi over 4 will be negative 1. Tan is negative in quadrant 2, but we can also see it from our coordinates. If you did sine divided by cos, root 2 over 2 divided by a negative root 2 over 2 will give you a negative 1. Quadrant 3, well, cast rule says tan is positive in quadrant 3. If we look at our coordinates, negative root 2 over 2 divided by negative root 2 over 2 would give us a positive 1 as well. And finally, in quadrant 4, tan of 7 pi over 4 will be negative 1 as well. So the special triangle for pi over 4 or 45 degrees is an isosceles triangle, and we are able to figure out sine, cos, and tan because isosceles triangles have two sides that are the same. And once you have that, then you can do a squared plus b squared equals c squared and get the values for sine, cos, and tan. Your next family is the pi over 6 family. And actually, the special triangle for pi over 6 is the same as the special triangle for pi over 3. So in this space, we will draw the same special triangle for pi over 6 and pi over 3. What does it look like? Well, if I draw a 90-degree triangle and I label one of the angles as 60 degrees, thinking I'm going to draw a special triangle for 60 degrees, and it needs to be a right-angled triangle in order to do sine, cos, and tan from that triangle. The other angle that's left has to be 30 degrees so that it adds up to 180. Now, when you think about special triangles in trigonometry, you think about isosceles because it has two sides the same. You think about equilateral because it has three sides the same and all three angles 60 degrees. What do we call this triangle where all the sides are different and all the angles are different? Do you remember? It's like, if all the sides are different and all the angles are different, is it really special? This is like not special triangle. But I guess they felt bad for the not special triangle, so they gave it a name as well. The name of the not special triangle? Scalene. Do you remember that? Right? You heard it, and then you forgot about it because it wasn't special. Right? And it's just like they just gave us a name so we wouldn't feel bad, but this triangle feels terrible. There's nothing special about it. Do we know anything about the sides? No. All we know is that they're all different. So this triangle was walking around sad because it's not special, runs into another triangle just like it, not special, and they're like, I'm not special. And the other triangle said, I'm not special either. So they're like, well, you want to hang out? So they said, okay. So these two not special triangles decide to hang out, and here's the other one. It's also got 60 degrees and 30 degrees. But when they were hanging out together, all of a sudden, they became special. What's special about them together? If you put it together as one big triangle, it makes an equilateral triangle. So if it's an equilateral triangle, well, that means that if I pick an arbitrary number, let's say I say this side is length 2, well then this side is length 2, and the whole bottom together would make a length of 2, meaning this side would be 1 and this side would be 1. And if I have values for those sides, I can now do a squared plus b squared equals c squared. Do the mental math. What will you get for the other side? Did you get it right? Square root of 3. Now we were able to get all of those values without the use of our calculator, and now that we have those values on there, we can figure out what sine of 30 degrees what cos of 30 degrees and what tan of 30 degrees are equal. We can also figure out what sine of 60 degrees, cos of 60 degrees, and tan of 60 degrees is equal to. Sine of 30 degrees. Look at your 30-degree angle. What's the opposite side? What's the hypotenuse? 1 over 2. Cos of 30 degrees. What's the adjacent side? What's the hypotenuse? Tan of 30 degrees. What's the opposite side? What's the adjacent side? And again, here we will rationalize. And tan of 30 degrees is root 3 over 3. Sine of 60 degrees. Look at your 60-degree angle. What's your opposite side? What's your hypotenuse? Cos, what's your adjacent side? What's your hypotenuse? Tan, what's your opposite side over adjacent side? And so from that special triangle, we not only get all of our ratios for sine, cos, and tan of 30 degrees, we get all of our ratios for sine, cos, and tan of 60 degrees. So now if we go back to our 30-degree, we start off with what's easy. Reference angle of 30 degrees all the way through. That means in quadrant 2, if it has a reference angle of 30 degrees, that angle's 150. Give you a 5-second head start to do the other two. How did you do? Did you get 210 degrees and 330 degrees? Now moving on to radians. 30 degrees is pi over 6. Remember the shortcut for changing from radians to degrees? You can change the pi to 180. What's 180 divided by 6? 30 degrees. Pi over 6. In quadrant 2, you'd have to go pi minus pi over 6. Again, how do you subtract fractions? You need a common denominator. In quadrant 2, it'll be 5 pi over 6. Ten-second head start for the other two. How did you do? Did you get 7 pi over 6 and 11 pi over 6? Draw the coordinates where those angles intersect your unit circle. Points on the unit circle are cos theta comma sine theta. So if we look at cos of 30 degrees, it's root 3 over 2. Sine of 30 degrees is 1/2. And once you know quadrant 1, since all of those have the same reference angle, they'll all have the same values. The only thing that'll change is in quadrant 2, your x-coordinate's always negative. Your y-coordinate's always positive. In quadrant 3, both of your coordinates will be negative. And in quadrant 4, your x value will be positive, your y value will be negative. Now, for tan, from our special triangle, we figured out that tan of 30 degrees, or tan of pi over 6, was root 3 over 3. That was after we rationalized it. tan is also sine divided by cos. And if sine is your y-coordinate and cos is your x-coordinate, can you see how you would divide that? What's your rule for dividing a fraction by a fraction? No, it's not give up. Multiply by the reciprocal. So if I have a fraction divided by a fraction, this is the same as 1/2 multiplied by 2 over root 3. Can you see that your 2's would simplify and you'd get 1 over root 3? And then if you rationalize, just like we rationalized before, you would get root 3 over 3. And if you know tan in quadrant 1, well, then you know tan in quadrant 2. Tan of 5 pi over 6 is negative root 3 over 3. In quadrant 3, tan of 7 pi over 6 will be positive root 3 over 3. And in quadrant 4, tan will be negative again, negative root 3 over 3. So you're now ready to do some mental math. Okay, you might have to flip between the two pages. You can use your circle that you've drawn here on the first page and the second page as a cheat sheet. We're going to start off with tan of pi over 4. And David's going to pick our first volunteer. Azar, what is tan of pi over 4? So you can look at the front page. You can look. I'm asking you what tan of pi over 4 is equal to. One. Perfect. Pick our next volunteer. What is sine of 7 pi over 6? Oh, the revenge volunteering. Nice. Sine of 7 pi over 6. No, that would be tan of 7 pi over 6. We want sine of 7 pi over 6. Now, using your big idea, sine is a coordinate on your unit circle. Is it the x-coordinate or the y-coordinate? Sine is the y-coordinate. It'll be negative 1/2. Sine of 7 pi over 6 is negative 1/2. Perfect. Pick another volunteer for cos of 270 degrees. Can't pick the same person twice, so you guys are now off the hook. Who did you pick? AJ. Cos of 270 degrees. Zero. Perfect. So you look at 270 degrees, you look at your x-coordinate, and it is 0. Okay, pick someone for cos of 11 pi over 6. Carson. Cos of 11 pi over 6.
Square root 3 over 2.
Perfect. Square root 3 over 2. What is tan of 30 degrees? Pick a volunteer. Find 30 degrees. Find your tan value. Square root 3 over 3. Because 30 degrees is the same as pi over 6. We labeled it on here as tan of pi over 6. But that means the same thing as tan of 30 degrees. Square root of 3 over 3. One more. Let's do, how hard do you want to make it? Not too hard? No, then the last person is like, I was going to do sine of 13 pi over 6, but I'll make it easier. I'll just do sine of pi over 6. So Callan, pick someone for the last one. Sine of pi over 6.
I love cans.
1 over 2. Now, if I had done sine of 13 pi over 6, you would have to figure out where 13 pi over 6 ends. And 13 pi over 6 is the same as 12 pi over 6 plus pi over 6. And the reason I'm writing it that way, would you agree that 12 pi over 6 plus pi over 6 would be 13 pi over 6? And 12 pi over 6 is the same as 2 pi plus pi over 6. And if I did that in standard position, 2 pi would be all the way around plus pi over 6 more. It would be coterminal with pi over 6. So sine of 13 pi over 6 would still be your y-coordinate and would still be a half. Okay, let's finish up with our last one. For this one, I'm just going to give you quadrant 1. The reference angle is 60 degrees in degrees. Pi over 3 in radians. Your coordinates here are 1/2 because cos of 60 degrees is 1/2. Sine of 60 degrees is root 3 over 2. And tan of pi over 3, or tan of 60 degrees, is root 3. There's your head start. Do all the rest. Check to see how you did with your degrees. Check to see how you did with your radians. Check to see how you did with your coordinates. Finally, check to see how you did with tan.